Welcome everybody, I hope you are doing well today's lecture. We are going to talk about the panel connection. So go get your drink and let's begin with this lecture. First of all, this is the normal IV curve. There are two types of connection in PV modules together. First type of connection is series connection. The second type is parallel connection. The type of connection is going to vary the IV curve and stretch it, whether in voltage direction or in current direction. If you want to increase the voltage of the PV system, you will need to connect it in series connection. And if you want to increase the current, you will need to connect it in parallel connection. Both types is going to increase the powers of the PV system by adding more PV modules. Now we have understood there are two main types of connection. The first type is the parallel connection and second type is series connection. Also, we can connect the PV modules together, series and parallel. Let's start with the first type, connecting two PV modules together in parallel. How are we gonna do this? Each PV module has two terminals, positive terminal and negative terminal. When we connect the positive terminal of the first PV module to the second module positive terminal together, and the negative terminal in the first to the second negative terminals, and take the voltage from the positive one and the negative one to continue, this connection is called parallel connection. This type is basically very important to help you increase the current of the PV system. This method of connection has multiple advantages and disadvantages. One of these advantages, it helps to control the voltage while generating the system current. Also, it has multiple disadvantages, like it's used with the same voltage value. If you have a multiple PV system, PV modules connected together in parallel, all of three must be having the same voltage to be connected in parallel. If they have different voltages, the output voltage is going to differentiate and get the lowest value, as we're gonna describe in the next example. It can cause a high current if there are too many connections. One of the most important and hard disadvantages of the parallel connection is high amperage is difficult to travel long distance without using a very thick wire. So the temperature will increase and the voltage and power will decrease in the parallel connection. One of the most disadvantages of this PV system is if there is shading on any part of the system. Let's say there is shading on any part of the PV system connected in parallel. This will cause a lower voltage on this part or the shaded PV panels. This will cause the shaded PV panels act like a diode and is going to be reverse biased, which is going to damage the shaded PV panel. To overcome this problem by adding a series diode in series with PV panel to prevent the reverse current from occurring in shaded place. One of the disadvantages of this solution is the constant loss at the diode is going to reduce the output voltage. Another solution is to use a magnetic field sensor to detect the reverse current and activate the power separation switch to separate the shaded PV panel. Let's take an example of paralleling. First example in paralleling is if you have a different PV panels connected in parallel, like these 4 PV panels. Each PV panel have power of 152 watt and 19 volt and 8 ampere. The total voltage of the parallel is going to be the same voltage around these 4. So the voltage here is going to be 19 volt, voltage here is 19 volt, voltage here is 19 volt, so the voltage here is going to stay 19 volt. So the voltage was going to stay constant in case of parallel. What is going to happen is increasing of current. As this current is 8 ampere, is going to be sum with this 8 ampere and give us 16 ampere. Then sum with this 8 ampere, we are gonna get now 8 plus 16 is going to be 24. 24 plus 8, we're gonna get 32 ampere. So the total current of the parallel system is going to times number of PV module connected into parallel times the current of each module. We're gonna get 4 times 8, we're gonna get 32 ampere. And the total voltage is going to be 19 volt. In this case, the total power is going to be 19 times 32, we're gonna get 608 watt. 608 watt for the perfect 4 typical PV module. What would happen if there is shading on the first PV module? If there is a shading on the first PV module, of course the total power is going to be reduced. How is going to be reduced? First thing, the voltage around the first module is going to be reduced to 17 volt. And the rest 3 is going to stay as 19 volt. The output voltage is going to be forced to be the lowest value, so the voltage here is going to be forced to be the 17 volt. Okay. The total current is going to stay constant. 8 times 4 is going to be 32. Now the total power is 17, which is a voltage, it has been reduced. Times 32, we're gonna get 544 watt. In this case, there is 664 watt losses compared to the previous one, or 11%. Let's see another example. What would happen if the second one has been shaded with a different from the first one? And the current in the first one is going to be different than the second and one and third one and fourth one. The first thing, the voltage is going to be the lowest value. In our case here, is going to be 17 volt. So the voltage is going to be keep at 17 volt. What will happen for the current is going to be summation for each current. 8 plus 8 plus 7 plus 5, so we're gonna get about 28 ampere. Now, the total power 17 times 28, we're gonna get about 476 watt. This means about 132 watt losses compared to the original case, or 22% of the installed power. The second type of connection is the series connection. As we said, each PV panel has a positive and negative terminals. Positive terminal and negative terminal. Positive terminal and negative terminal. Positive terminal and negative terminal. When we connect the positive terminal to the negative terminal and positive terminal to negative terminal and get with these two, this connection is called series connection. In this case, the current in the entire 3 PV module is going to stay constant. On the other hand, the voltage across the output is going to be summation of these voltages, according to Kirchhoff voltage law. What is the main problem with the series connection? The main problem with the series connection is shading, which may cause shaded cell damage. In the case of local shading on the solar cell due to dust, for example, the presence of dust on solar cell means there is a shadow on it and less radioactive radiation, and this means less photon is going to fall on the PV cell, causing a less electron hole pair, causing less power produced by this PV module. When the current of any cell is reduced by shading, a reverse voltage is going to be forced on this PV module and occurring the cell and its voltage to be damaged. What we are gonna do is, by adding a parallel diode on the PV module, this parallel diode is going to force, if there is any shading on this PV module, to the current to flow easily through it without any reverse bias to the load. Let's take an example on series connection. If we have 4 modules, each module have 152 watt and 19 volt, 8 ampere, the total current is going to stay constant as they connected in series, so the total current will stay at 8 ampere. Okay, the total voltage is going to be summation of these voltages. So 19 plus 19 plus 19 plus 19, we're gonna get 19 times 4, we're gonna get 76 volt. So the total power generated by these PV modules is going to be 8 times 76 volt is going to be 608 watt. Same to the previous example. Now, what would happen if we have shading on the first one and the power reduced to 136 watt and the voltage reduced to 17 volt? First thing, the current is going to stay constant, so this is constant current is going to be 8 ampere as it. But what will happen is the voltage is going to be reduced. 17 plus 19 plus 19 plus 19, so the total voltage is going to be 74 volt. This means 74 times 8 ampere, we're gonna get 592 watt power, or 16 watt lower power from the installed version, or 3% losses in the installed power. The next example, what would happen if we have 2 PV modules with lower power due to shading? The first one is 85 watt, the second one is 126 watt. The current is going to be forced to the lowest value. So the lowest value for the current is going to be 5 amperes. So the total current is going to be 5 ampere. But what would happen for the voltages? According to Kirchhoff voltage law, the 17 plus 18 plus 19 plus 19, we're gonna get 73 volt. Total power is going to be 73 times 5, we're gonna get 365 watt, or 243 watt lower wattage compared to the installed power, or 40% losses. Let's talk about the last type of connection when we connect series plus parallel in the same time. In this case, we typically connected 2 PV module in series. The connection in series is called string. So this is called string. We have here 4 strings. Each PV module has 152 watt and 19 volt and 8 ampere. So the voltage across the entire system is going to be the voltage over 1 plus the voltage over 2, according to KVL or Kirchhoff voltage law. So 19 plus 19 is going to be 38 volt. But the current here is going to be 98 ampere and 8 ampere and 8 ampere and 8 ampere. The total current for these four strings is going to be 8 times 4, we're going to get 32. 32 times 38, we're going to get about 1,216 watt. So connecting series and parallel is going to increase the power of the system. Also, you will need to keep in the mind, if any shading happened, is going to force this PV module to operate at less power and less voltage. This will cause the system power is going to be reduced. This is called shading losses. Okay guys, that's for today. Thank you for watching. Bye bye.